Okay, so today is a slightly different week compared with the last few weeks and the next couple of weeks because we don't have the student presentation. Also, I guess for some people, a holiday week. So thank you to those of you who aren't on holiday. It's nice to see a few people here. Okay, right, so we're going to actually change topics today. For the last few weeks, we've been doing model checking of forms of temporal logic in different scenarios. Model checking is used to verify properties, as we've seen, and properties expressed these modal logics, that is temporal logics that we've been looking at, of normally finite state systems, because you need to check a finite model, and so it needs to be a finite state system. There is an area of model checking, automatic model checking of infinite state systems, which is also an interesting area in its own right. In my view, it's a bit limited. The kind of infinite state systems that you can deal with are quite restricted. It could have been something to include in the course, but I decided not to. So instead, what we're going to do over the next 3 weeks is something to do with verifying infinite state systems. But this is also known as program verification, because we're going to verify computer programs written in a programming language, and we'll look at the techniques that we have for doing such verification. So they're infinite state systems because a computer program in general cannot be described by a finite state machine, a machine with just a finite number of states and transitions between them. Okay, so what we're going to do for half of today, I think everyone, at least most people, will have seen before, but we need to do it in preparation for what's going to follow. So the main theme of the next 3 lectures is program verification. And there's a whole methodology for this based on some very influential work, seminal work by Tony Hoare in the late 1960s, which has then been developed in further, more practical directions and is now a very, very important technique in real practical examples. There's a whole lot of work going into this. But we're going to start with the basics today. So what we're going to, and in fact, the 2 main topics we're going to cover in this part of the lecture, we're going to start with what's called Hoare logic, after Tony Hoare, but was professor at the University of Oxford, also the inventor of the quicksort algorithm, had many contributions to computer science. And this is a very simple logic for verifying very simple imperative programs. But simplicity is a good thing here, because the simple logic that the kind of simple imperative programs one verifies involve the sorts of constructs that exist in real-world programming languages, and Hoare logic then forms a basis for extending the verification technology to more real-world languages. And we're going to look at a particular, in this course, we're going to focus on a particular extension of Hoare logic, which has been very influential over the last 20 years or so, and it's currently, there's a huge amount of work going into it, and this is something called separation logic. And these are, and this, so separation logic builds on for logic. And these are logics for verifying program. It's not required that you've seen for logic before, but I expect quite a lot of people have. So just to get a feeling for it, I think I asked this in the first lecture, but anyway, I've forgotten the answer. So how many of you have seen for logic before? Okay, not everyone. How many of you have seen it in more than one course? Okay, so it appears in, maybe most of you saw it in like programming languages Ishurama at the undergraduate at Andre Bauer's course. Yeah, if he was teaching it that year, I don't know. Yeah. But it also comes into a couple of other courses. Okay, anyway, it doesn't matter if you haven't seen it before. What's disappointing about it when you first see it, although you shouldn't be disappointed because you need to start with very basic things, but we're going to be verifying very basic programs. And so we can do them on the whiteboard for one matter. So here's a simple program. So it's in an imperative language. This is the assignment statement to variables. And going to do a while loop. And in the while loop, we're going to increment y. Just write y plus plus. Anyway, multiply z by y. That's it. Sorry? Oh. Yes, we do indeed have an x, but we don't define it. So x is the input. Very, very good question. X is the input. And then what does the program calculate? I suppose, so z is the output variable here.
X factorial.
So indeed, x factorial. And this is almost everybody's first introduction to for logic, a program like this. So this calculates the factorial, and there are various ways of seeing that. And in ancient times in computer science, like the 1960s and 1970s, people were very concerned in how actually do we precisely define what a computer program does. And there were two main approaches to answering that question. One was called operational semantics. In operational semantics, you define how a program behaves by giving, for example, some notion of abstract machine, like a kind of computer that you run the program on, and explaining exactly the steps of execution that a program takes, and that defines how the program behaves. It's very concrete, it's very much program does this because it behaves in this very specific way. Another approach is called denotational semantics. In denotational semantics, so semantics means meaning. You're trying to define what a program does. The denotational idea is, well, let's do things at a much more abstract mathematical level and just state mathematically what the effect of executing the program is. So in this case, the appropriate denotational semantics would model these kind of programs, essentially working on a memory state where you've got some variables, site values. It'll take a starting memory state, and then if it terminates, we'll produce a resulting memory state. Yeah, that would be the denotation. Tony Hall thought that was a bit abstract. So Tony Hall proposed a third approach to defining what a program does, which he called axiomatic semantics. The axiomatic semantics is you give axioms and rules for specifying essentially the logical behavior of the program in terms of what it does to properties you specify in the program you might like the program to satisfy. And so he viewed Hoare logic, which we're going to see in a moment, as a way of precisely defining what a program does. Irrespective of whether or not you think it's a good way of defining what a program does, an important aspect of it is that Hoare logic is going to give us a logic for specifying properties of programs, and it's going to give us proof rules for verifying that programs satisfy those properties. And then the program verification is you specify what you want a program to satisfy, you follow the proof rules to prove that the program satisfies it, and lo and behold, you've proved that your program does what you want. And so Hoare's approach to program logic, only one, always has this problem. Is the other one on the table or chair somewhere? Anyway, it doesn't really matter. We can cope with one. Anyway, Hoare's approach was to say, and it was a very beautiful idea, and this has been really influential in throughout the years since. So Hoare introduced the notion of a program specification in the following form. You write a program, and one often uses C for a program because these very simple imperative languages people call programs commands. It's a command that alters the state. So here we could write a program like this. We want to specify the properties of the program. And what we do is we use two logical formulas. So this is called the precondition, and this is called the postcondition. And the idea is that these logical formulas will be formulas in first order. Let's suppose we've got integer variables. They're going to be formulas in first order logic, or even some richer logic if you like, where you have integer variables and you have whatever language you need for expressing the properties you want of integers. We can allow ourselves an ordinary mathematical language for that. And so the way you read such a specification is we want to specify what this program does, and we can specify it in terms of if we run the program in a state satisfying the precondition, then the logic will guarantee that if we use the rules of Hoare logic, it will guarantee that the result of running the program produces a state that satisfies the postcondition. So if we run C, so this is the meaning of the Hoare triple. So such a thing is called a Hoare triple. Because there are three components: the precondition, the program, and the program. Postcondition. And it says if we run C in an initial state S satisfying phi, then the end state, final state, after executing C satisfies psi. Well, I've been a bit imprecise here because there are some subtleties involved about whether the program terminates or not, which we'll come back to. So let's specify what happens here. And as a first specification, I'm going to, let me just we're just going to say in any state, in any input state here, we run this program, and at the end, we're going to be in a state where Z is the value of X factorial. Okay? There's actually a bit of an issue here because we're assuming we're assuming the programming language is dealing with integer variables. If we run a state in which X is a negative integer, then this program is not going to terminate. Okay, but nonetheless, we can make this specification because there's a way of interpreting the specification. There are actually going to be two ways of interpreting a specification. Maybe it's actually better to just rub everything out and start again. So there's going to be there are two ways of interpreting the specification. There's what's called partial correctness and total correctness. Partial correctness says if C is executed in start state S and S satisfies phi, and if C terminates, the execution of C, this execution terminates, then the result state satisfies psi. Total correctness says the same stuff. If C is executed in the start state S and S satisfies phi, but it gives us a stronger property that if we start in a precondition satisfying phi, it gives us the property that the execution does terminate. So then the execution terminates. And the result state. So we have the common idea of a Hoare triple, which is the specification. We have two different possible ways of interpreting a specification. In one way, we leave proving the termination of the program as a separate task. It's not addressed by Hoare logic. Hoare logic just says that under the partial correctness interpretation, Hoare logic says if execution terminates, then the resulting state satisfies the post condition. Under the total correctness interpretation, the logic will actually guarantee termination. So you don't need to separately prove termination. if we manage to prove in the logic the total correctness, then that proof gives us termination. So there are two flavors of Hoare logic. So this specification is correct for partial correctness. Because what does it mean for a start state to satisfy true? Well, every state satisfies true. So this says if we run the program in any start state, then we want partial correctness, and if the program terminates, then this holds. Because if the program terminates, it will be the case that x is not a negative integer. So x is a natural number, and z will be factorial. If we wanted a total correctness specification, we would have to say total correctness specification would be that if x is greater than or equal to 0, then at the end z is x factorial. This is total correctness. Okay. And at the beginning of the lecture, I motivated this as moving away from the situation we've been in model checking in the past few weeks, where we've been dealing with finite state systems. So in what sense is this not a finite state system? Can anyone?
Infinite many possible values, for example, for x.
Yeah, so variables can take, I mean, assuming we don't have max int or something like that, but at least theoretically, variables can take infinitely many values. And our states here are program states, which are mappings from variables, and our simple model will be a mapping from variables to values, to values. And there are infinitely many such states. And this program itself, I mean, depending on what start state you started in, but if you started it in a negative, if you started it with a negative x, it would actually visit infinite, the execution would in fact visit infinitely many different states. I mean, obviously, whenever a program terminates, it can only visit finitely many states, but termination is a non-trivial property of programs. Right, so we're going to actually verify this program using Hoare logic. So that's the main job of the remaining 20 minutes of this hour.
Yes, for decimation, when for total correctness, we usually use the square bracket instead of the brackets.
Who's we? Who's the usual we? Okay, well, so in that course you do, but people tend to use curly brackets just in all. I mean, it's not that's not a standard distinction. So I'm going to have, if the specification is written in the form it's written, and we might consider the partial correctness interpretation or the total correctness interpretation. Right, so to verify the program, I'm actually going to do it a bit of a painful way for the first one, and then we're going to do another program a less painful way, I guess, after the break. And the less painful way is the more important way, but to begin with, you need to see the painful way. So W is going to be notation for the while loop part of this program. So for while y is not equal to x, do y, increment y, and multiply z by y. And then de fact, the factorial program is we assign 0 to y, we assign 1 to z, and then we do this while loop W. Okay. And we want to verify, so let's put this at the bottom of the board. We want to verify the Hoare triple. We're going to have proof rules that will allow us to do the verification. We want to verify that the p factorial program, after running it, we end up in a state where z is x factorial. Okay? So how do we prove such a thing? Well, we have proof rules that tell us what to do for each of the constructs that we can use to build up a program. So what kind of constructs do we have in our program? Well, we have assignment statements. We have, well, this semicolon, it's like the end of a statement. That's how one thinks of it. But then you can also view it as an operation on programs, that is, you're sequencing two programs together. So here we've got the program that's just assigned 0 to y, then we're sequencing that to the remaining program. And here so it's basically saying run this, then run this, then run this program. Yeah. We've got sequencing, we've got assignment, we've got sequencing, and and in this program, the only other thing we've really got is the while. So for each of these constructs, we're going to have a proof rule. And the proof rule for sequencing, so maybe we don't need to program on both boards at once. And the proof rule for sequencing is if we want to prove that the sequencing of two programs satisfies this Hoare triple, if we start the sequencing with the sequence commands, we start within a state satisfying 5, and if running them terminates, so we're going to just deal with partial correctness for the moment, then the result state satisfies psi. Well, how can we break that down into something simpler? And now we come to a very important principle on which Hoare logic is based, which is the principle of compositional reasoning, which is in order to verify a complex program, so this is built out of two parts, you break it down into the two parts and you verify appropriate parts of each, appropriate properties of each of the parts, such that where those appropriate properties need to be chosen, so that verifying those properties separately for each of the parts gives you a verification of what you want, that the sequence command satisfy this specification. So in this case, well, how can we do that breaking down? Well, there's a very obvious way for sequencing, which is if we can find some intermediate property theta, say, that when we run C1 from a state satisfying 5, theta holds, and when we run C2 from the state satisfying theta, psi holds. If we can prove this and we can prove this, well then that's good enough to prove this. So it's very intuitive. So here, we want to verify that p factorial satisfies this specification. Well, p factorial is a sequencing of, well, there's a question how we bracketing the sequencing, which is actually a boring question, so let's not go into it. I'm going to take the first two components off at once and then sequence. I mean, sequencing is associative anyway. So we're going to prove a specification for this first bit, which is kind of trivial. So the specification for the first bit is going to be that if we do y, if we assign 0 to y, and then we assign z to 1, sorry, assign 1 to z, and that's not in specification, then guess what the post condition here is going to be? What properties hold after we've executed this? Yeah, y is 0 and z equals 1. I'm just going to write commas instead of and here, so y equals 0 and z equals 1. Which is the formula. Okay. So it's a bit. And then we want to prove that y equals 0 and z equals 1. We start in that situation and we run then the while loop, then we get that z is x factorial. Okay. So how do we prove the property of a while? And this is the most important rule of whole logic. So how do we prove a property of a while loop? So a while loop has this form. D here is the condition. So that's, that returns a Boolean. This is condition. Boolean valued. And this will be something called an expression, but this is an expression that calculates to a Boolean. Something like y is not equal to x. That's, and this is the command, the while of the loop. So how do we? So it's a well, the important thing. It is a command. So how can we prove property of a while loop? Now the thing about while loop is you're going to execute C several times, but you don't know how many times you're going to execute it. Depending on when this test becomes false, I mean, you're going to execute it while B continues to be true, but at some time B is going to become false. So you don't know how many times you execute it. So what you do is you look for something called an invariant property of the while loop. And let's call our invariant eta. So we're going to look for an invariant property. And by an invariant property, we want the condition to hold that if we execute C in the invariant property, and in a state satisfying the invariant property, then we get the invariant property back. And that means that if we run the while loop in a state satisfying the invariant property, however many times we execute the while loop, we're going to get the invariant. So this is an eta. So however many times we're going to run the while loop, we're going to get the invariant property back. Okay. But when we execute the while loop, we also know something more. Again, I'm going to use comma for and. We also have that we execute the while loop. We execute because the B condition is false. So we also have that not be false. And moreover, the invariant property, well, we're only actually going to execute this C in the case that when we do a while loop, we test to see if B is true, and if so, we do C, and then we test again, and if so, we do C. So we only actually execute C in the case that B is true. So actually, we don't need to show that C always preserves eta, it only needs to preserve eta in the case that B is true. So this is the rule for the while loop. And this eta is called the loop invariant, or just the invariant. And this is a rule for partial correctness because we're not proving termination in this. So this is the rule we're going to need to modify if we when we have a system for total correctness. But this is a while rule for partial correctness. Okay. So we want to prove this property, that if we start in y equals 0 and z equals 1, then, and we do our while loop, then z is x factorial. But we can't apply this while loop, we can't apply this while loop rule, because it's not the specification, the whole triple we've got here is not of this form. There's no invariant property on the left and right side. So we need to, so our verification task becomes, we want to then change this into a form that we've got the invariant property. And to do that, we need to see what the invariant property of this rule is. So what are the properties? What is the property that if we're in a state before we execute the while loop here, and we come out the other side, what property still holds here? And the answer is, it's a tricky question, or then, well, I mean, if one of you can see it off the top of your head, I'll be impressed. But an answer, you need to think about these invariant properties. It's a bit like finding an induction hypothesis and an inductive proof, and in fact, there's a precise analogy that one can make between them. So the appropriate property here is that if z is y factorial and y is greater than or equal to 0, and we run the while loop, then when we come out the other side, it will hold that z is y factorial and y is greater than or equal to 0, and moreover, y is not equal to y is not equal to sorry, yeah, it's not the case that y is not equal to x, and then y equals x. Okay. So we want to get this rule into this, we want to get our specification into this form. And we can do that because there's an important rule called consequence rule, or the implication rule, which says whenever we want to prove, so I'm writing the rules like this, like we were doing in logic in the first part of the course. And the way to always read them is whenever we want to prove this, well, then we need to prove what's above the line. I mean, we don't need to, but we can prove this by proving what's above the line. And one rule that we can use, called the consequence rule, is that we can change the properties, the precondition and the postcondition phi and psi, if it holds in the integers. So it's a true property of the integers that phi implies phi prime, and it's a true property in the integers that psi prime implies psi. So here I'm writing this to mean these are true properties of the integers. Okay, so we need some mathematical implications. The reason for this is, well, we need to argue that if we're in a state satisfying phi, then we end up in a state satisfying psi. So suppose we're in a state satisfying phi, well then by this implication we're in a state satisfying phi prime. So if we prove the premise, we end up in a state satisfying psi prime, and then by that implication we satisfy psi, so everything works out. So here we've used sequencing. used the while, here we've used consequence. And now we're in a position that we can try and prove the while. And here, what have we used for this? Well, to prove this, or we haven't finished that proof yet. There's a simple proof for assignment, which is that if we want to prove, so we've got an assignment. So an assignment is going to be of this form. We have some numerical expression that will calculate to, and it will calculate an integer. We assign the value to x. Well then, whatever property phi we have as post condition here, we can derive that from, if we substitute e for x. Was I using in logic, was I using this notation for substitution? Does anyone remember? Here we're substituting e for x in phi. Good. So, oops, it's getting a bit crowded on the board. So this is phi with e instead of x. And the reason for this is, well, suppose we assign e to x and we look to see if phi holds. Well, when we're checking to see if phi holds here, x always has the value e. Okay? So how do we know that the state will, we've changed the state from the start state by modifying the value to e. How do we know that x, how do we know that phi holds here if x has the value e? Well, we can get that's true if in the original state, wherever we had x in this property, x will have a different value here, but we forget, instead of looking at the value of x, we replace that with the value p. Okay? So it's a very simple way of essentially one moves the property from the post condition to precondition with a substitution. So here, well, we'll actually first we need to, this is a sequencing, so we need to find an intermediate property. Now this is not quite of the right form, but the right form for applying that rule okay, so I'll put a line above here because the assignment of y 0 to y, this specification is directly an instance value of this rule. So this is the assignment. And how do we justify this? Well, this is logical consequence rule because this, so here the empty specification means true, and true implies 0 equals 0, of course. So this is again the consequence rule. Okay. Right. We still have to deal with now proving the while loop satisfies this part of the specification here. So as I said, we're doing things the painful way, and I'm writing out all details. But after this, we'll see a less painful way of doing things. So I suggest, even though we don't have presentations, we still aim for the same break format as before. So we finish. Do you have your lecture at Hoare?
No.
Oh, they're kind of Hoare. Sorry?
Yeah, that kind. So.
Okay, right. Well, in that case, is it okay to have a 10-minute break? Or even, or 15-minute break? How about a 15-minute break? Okay, so we'll have the proper break then. Okay, so we're halfway through the verification of the factorial program. As I said, it's a bit painful. There's lots to write. We're filling out these rules. What haven't we done? Well, so here I finished off the proof of this absolutely obvious fact using two rules, the consequence and the assignment rule. A similar proof will give us a proof of this absolutely obvious fact as well. And the more interesting thing is verifying the while loop. So let me just do one rule here. Oh, I've actually rubbed off the while loop. But once we've got so eta is this conjunction, our invariant property. And here we've got eta and not b. And what we need to verify here, so here we go to the while loop, the while rule. So here we need to verify eta, which is this conjunction, eta and b. So b is y is not equal to x. And then the body of the while loop, the actual command part of the while loop, which order was it? So something got incremented, and then I think the increment. Sorry? Oh, yes, excellent. So y is incremented, and z is multiplied by y. And we need to show that the invariant property is indeed invariant, so that stays invariant. So that's the first step. Well, and now we've just got two assignment rules to put in. So I've got the sequencing and two assignments, but I'll let you fill that in for yourselves, and there will be LaTeX lecture notes for today's lecture where you can view. But anyway, it's an exercise to complete the proof. As I say, it's a very tedious writing thing to get these big proof trees. You have to write lots of things multiple times if you're writing in this style. So we don't really want to do this style of program verification. So, but fortunately, there's a nicer way of doing it. It's better to use what we call the tableaux style. So this is better to use something called the tableaux style instead. And in tableaux style, you have your program text and you basically annotate it with statements that hold at this point in the execution of the program. You need to annotate it in a way that's governed by the proof rules. And if you annotate it following the proof rules, you then verify correctness. So that's what we're going to see, and we're going to do it on a different program. And so the program is this. So while x is not equal to y, do. This one's going to involve also a conditional statement, and if then else. So if x is less than y, then. Whoops, something, then we're going to subtract x from y, and else, so in other words, if y is greater than equal to x, we're going to subtract y from x rather than subtracting x from y. Okay, that's the program we're going to verify. I should have left space for the specification. And I want to verify this using the tableau style. And in order to avoid all the messy writing on the board, I prepared slides for this. So we're going to let's clear the board. But while I'm clearing the board, I'd like you to think about this program and tell me what it calculates. So the output variable, the input variables are x and y, and the output variable is x. So it's calculating a function on integers. And it's an algorithm you will all know, but you might know it in a more efficient form. This is a slightly inefficient version of it. Doesn't really matter. So the question is, what value are we calculating? So we have y and x at the start of the program, and then x at the end of the program is an important value associated with y and x. Oh, doing things in the wrong order because we needed to put the projector in. I was supposed to do that and then be cleaning the board while it was warming up. Anyway. Right, so does anybody know what it's calculating? Okay, so most people seem to be saying that the greatest common divisor, so it's Euclid's algorithm, although the more common version is instead of subtracting x, you take y modulo x. The remainder when y is divided by where y is divided by x. So that's much more efficient. So if you take the remainder here you're going down much less quickly, but nonetheless it still works. Right, so we want that's going to appear. Right, so the specification that we want to verify. Come on. Right. So the specification that we want to verify is well, I'm going to make the wrong specification first. So firstly, just to get things to work, let's assume that we don't want to be talking about divisors of 0, and we don't want to involve negative numbers. So let's make x, y greater than or equal to 0. And at the end, we want x to be the greatest common divisor. And y will be the same, but it doesn't matter. Let's just look at x. X is going to be the greatest common divisor of what? The problem is we can't say of x and y here, because x has changed value. At this point, x will still be the greatest common divisor of x and y. That will be true, but it's not saying something interesting that x is the greatest common divisor of x and y at this point, because x will equal x. So in order to be able to specify this property, we introduce what are called ghost variables. And those are variables that don't appear in the program. So we know that their value at the end will be the same as the value at the beginning. And we're going to say that we want x0 to be the ghost variable for x, y0 be the ghost variable for y. So we set some values at the beginning. x0 and y0 don't change in the program, so here we can say x is the greatest common divisor of x0 and y0. Okay, x0, y0 are called ghost variables. Sort of haunting the program, something. They don't appear in the program. They just play a role in the specification. Oops, I need to be on the right computer. Okay, so here we've got our program. And the point is we're going to verify this by annotating it with statements that hold at various points in the execution. So we'll begin with the specification, what we're trying to prove, and we want put just the right amount of space in that everything's going to fit in between. And yeah, what we want to do is use rules for annotating the program to go from the precondition to the postcondition. Although actually, it's easier to work backwards from the postcondition. We think what we need to get there, and we work backwards, and eventually we want to get to the precondition. And if we manage to get to the precondition, that's good. We've verified the program. Okay, so we're verifying a while loop. So in order to verify a while loop, we're going to need to do the we're going to need to find an invariant property, and the way one verifies. So what one does in the if we've got some property, some command C in the body of a while loop, the way the rule for verifying a while program works is that I'm going to use indentation as a way of showing what the scope of the statements are. So the while loop as a whole will involve a precondition and a postcondition, where so when we verified the while loop, the precondition will be let me just see exactly where I put things. Right, so remember with the while, maybe I should write the while rule. So the original while rule was so we can derive this this is a meter here. We can derive this specification for the while rule if we can prove that the inner body preserves the invariant and works whenever B is true. And so the post condition for the while rule as a whole needs to be of the form eta together with not B, and the precondition is just eta. And we can verify that if we can verify that C, we can give it a postcondition of C, we can give it the invariant property eta as its postcondition and a precondition eta B. Okay, so we're just kind of writing all the assertions here. We call these properties assertions, stating what's true at the state in a particular time, at the point in the execution that the property applies. Here we've got the main thread of execution, and here indented, we've got the property that's repeated as we go round and round the loop. Okay? So we need to be able to apply the while rule. We need to be able to have a precondition and a postcondition that involve an invariant property, which we don't yet have. But again, we're going to use the implication rule or the consequence rule, but we'll now call it implication in order to get between the two, in order to get things into the right form. So that should be the next step. Right, okay, we've got several. Right, so we've got two steps in one here. So we've got the implication property here. So now the implication means so this is the while rule in the tableau format, and the implication is simply if we have phi and phi prime, we can say if we're in a state in which phi holds, we're in a state in which phi prime holds, as long as in the integers the implication that phi implies phi prime is true. So the idea is we're always reading one of these conditions as saying it is true at the state at this point when I run the execution, at this point in the execution, I will be in a state that satisfies this condition. And here we have, we can use the implication rule. So I'm saying this is implied by the implication rule because this property implies this. So here we're using the implication that if x and y are greater than 0, and the greatest common divisor of x and y equals the greatest common divisor of x0 and y0, and x equals y, if that's true, if all that's true, then x is the greatest common divisor of x0 and y0. Okay? That's a simple mathematical property that we use. And so here we've got this in the right form. And then, you know, so eta is now x and y greater than 0, and the greatest common divisors are the same. So that eta also goes at the top before the while loop, and we decorate the if then, sorry, and after the while, we have the precondition and the postcondition of the C command. So those would be automatically inserted in there. And the second line is also justified from the first. It doesn't say so because it's implied. There's also an implication that if x is y, well, if the top line holds, then the second line holds. That's also a true mathematical implication. Okay, let me just see what. Okay, that's. I was just seeing if that implied was going to. There should be an implied appearing on the second line. Right. So now we've got. We need to fill in the middle part of the proof, and for that we need to deal with an if then else statement. So let me. So how do we verify an if then else statement? Well, maybe I'll again write it as a rule. Quite easy to understand what these rules say. So if we want to prove, so an if then else statement will have the form if B, then C1, else C2. And if we want to prove that that satisfies the specification precondition 5, postcondition psi, well, what we need to show is how do we get to the resulting state from the starting state? Well, it depends on whether B is true or false. If B is true, we'll execute C1 and we want psi to hold. If B is false, we'll execute C2 and we want psi to hold. So we simply say, well, no, if B is true, we're still in the state satisfying phi at that point because we haven't done anything to the state, but we're testing B. So we simply say that if phi holds and B is true, then we want, if we execute C1 from such a state, we want to get to psi. And if we execute C2 from the state where phi not B holds, so if not B is true, phi, and we're going to execute 2, and we again want psi. Okay, so that's the rule for if then else in the triple format. That in order to have the tableau version of that, well, we're going to be. So we're running. We can nest the program like this. So if B, then C1, else if B is not true, C2. And we want to say oops, let's leave a bit more space. How we can prove psi? Well, we can prove psi from phi if when we just put the condition for C2 here, by and not B, on the side, and the condition for B1, for C1 here, by B side. Okay, just like that. So we're going to see now we have just below the while, we have the precondition of the if then else statement, and this is the postcondition of the if then else statement. So we're going to see those statements reappearing around the two subtractions. So need to go here. Oops, I've gone in the wrong direction. Right, so those are. I wish I'd got a stick, but so they've appeared around the subtractions, and notice that in the else case, we've got the. So we were doing a test if x is strictly less than y. So in the if case, we've got x is strictly less than y. In the else case, that should be an x is greater than or equal. Well, okay. It should be an x greater than or equal to y, but we've assumed above that x is not equal to y, but still, formally speaking, I should have already put x is greater than or equal to y there, because it's the negation of y, because it's the negation of x is less than y. Okay. And now, here we've got an assignment, and there we've got an assignment, so we'll simply fill in the assignments. This assignment, we need to, well, we're assigning to x, so up here we're going to substitute x minus y for x, just using the assignment rule we had before. So the assignment rule now looks like if x, we've got x, we're setting the value of x to e, and we've got property psi here, then beforehand we're going to substitute e for x. That's the precondition for that. So this is how we decorate the proof for an assignment. So if I skip through, right, so there we indeed, from x and y greater than or equal to 0, we're asserting x minus y for x. So we have x minus y and y are both greater than 0, which means that x is greater than y is greater than 0. So I put a bit of logical simplification in there, where we had greatest common divisor of x and y before, we now have greatest common divisor of x minus y. But we still need to bridge between this statement and the one above, but it turns out that again there's a mathematical implication between them. And this is this mathematical implication is the meat of the mathematics of the correctness of Euclid's algorithm, of this version of Euclid's algorithm, because here there is something slightly mathematically non-trivial involved. So if the greatest common divisor of x and y is some number, which is here the greatest common divisor of x0 and y0, but let's just say if the greatest common divisor of x and y is z, and x is greater than y, so that's next to, those are the statements that hold next to where it says else precondition. Then if we subtract y from x, what we get in the subtraction, x minus y and y still have the same greatest common divisor z that x and y had before. Okay, so there's a little bit of very baby number theory in that statement. So now, the next thing is to notice we've got that implication. It involves a tiny bit of trivial mathematics. And there we are. So we've written implied there, so that is justified. And again, we're going to deal now with this assignment statement above. And again, it's just the same as before. And again, that's implied. Oh, and then we notice that that indeed the precondition of the while loop is implied from the original precondition. And that is the end of the proof. Okay, so it requires, so this is in pretty much in full detail. It requires quite a lot of work to get these get these things through, but still this is a much better style, I hope you'll agree, than the tree style writing on the board before. And in practice, this is how proofs are typically done. And they can, nowadays they are done for substantial programs and really applied, and separation logic is one of the main instruments. So the same style adapts to separation logic, and that's one of the main application areas, this form of verification, doing things in this style, but using obviously computer tools in order to do it. Okay, so let's see. Maybe I'll leave the screen on. So the next thing I want to do is just to talk about how we modify. So we've been dealing with partial verification. Sorry, we've been dealing with partial correctness, and now I want to modify things for total correctness. So actually, maybe let's try continuing with the slides while they're here. So oops. So this is just, there were 4 times we had an implied before, and I'm just extracting here what the mathematically true implications are that we were claiming were true in order to justify the proof. Well, actually, one of the important things to say about Hoare logic is, so Hoare logic provides the rules for verifying following the program structure, but in the end, you have these mathematical implications that these need to be true in order for the applications of the consequence rule, or where we were writing implied in the tableau proof, for those to be correct. It's necessary that these implications hold. Hoare logic does not provide a means for verifying these statements. So to verify these implications, you need to use mathematics. So Hoare logic works together with mathematical verifications of the implications, a separate mathematical verification of the implications that we're claiming to be true. So we've done that. Right. So far we've been talking about partial correctness. So partial correctness, I defined it earlier. Here's a more formal definition. We say that a Hoare triple, precondition phi, command C, postcondition psi. So phi takes, so C takes phi to psi. That's partially correct. So that's a partially correct specification if exactly what we had before, whenever we have a start state satisfying the precondition phi, if the execution of C from that start state S terminates, then it terminates in a state satisfying the postcondition psi. So that's basically what we wrote on the board before. Now the question is to relate this to the proof rules we've given. So I'm viewing that as a semantic statement of the correctness of an assertion. That's why that top line uses this symbol. This is the \models in LaTeX. And this is the symbol we've been using throughout the course to say formula is satisfied by a model. And so now it's, well, we don't need a model on the left. We're saying a formula, instead of a formula, we're saying a partial correctness specification is satisfied if is true, in this case, if the right-hand side there holds. But what I want to do is make a formal statement of the relationship to the proof system. So the proof system is this collection of rules that we use for proving things. So the rules were given in this format with the triples above the line and the triples below the line. And basically the tableau presentation is just a way of presenting the same proofs just in an easier to develop and easier to read way. But the proof rules are still the same. And the proof rules give us rules under which we can prove a Hoare triple. Namely, we can prove a Hoare triple if we have a tree in which we apply all the proof rules whose conclusion is that Hoare triple, and the tree, takes us back to axioms such as the axiom we had for an assignment statement, for example. So everything must be valid all the way through the tree. So we've got the relation saying a Hoare triple is provable, and the important statement is that our proof rules are correct. So there's a formal soundness statement here that if we can prove a Hoare triple, then it's actually correct. There's also a completeness statement, but we'll look at that later in the course. That's going to be like the last theoretical thing during the course, looking at completeness for program logics. Anyway, for the moment, the proof rules are sound. We can only prove correct assertions, but that is only true because we're making this partial correctness interpretation of the specification. In practice, partial correctness is very useful because quite often one really wants to separately know that the program terminates. So you don't, it's quite often termination is an easy matter. And sometimes anyway, you're happy that the program terminates, but you want to know it's doing the right thing along the way. That's what partial correctness is good for. For other times, termination is also a subtle property. And one of the things you want to prove is that you want to prove that the program is doing what it's intended to do, and it actually does really terminate. And so for that, we're going to change our reading of the Hoare triple to the total correctness definition. But it is no longer the case that the proof rules we've given are then correct. We won't have soundness for the proof rules we've got. They're only sound because we're currently using partial correctness. So for total correctness, maybe I'll just say what total correctness is again. So total correctness is we simply modify the statement before, the semantic definition of correctness of the truth of a Hoare triple, to now say that the execution of C from any state satisfying any state satisfying phi does actually terminate. So now we're including termination in what the Hoare triple says. And we're going to have a similar soundness result for total correctness. We're going to have, as long as we use the correct proof rules, which are the proof rules for total correctness. So that's for the last 10 minutes here. That's what I want to do. The proof rules for total correctness. And the main thing, the only proof rule we need to change is the while rule. Okay, so while is clearly the interesting thing here, because all the other constructions we've had, so if then else, sequencing, assignment is just a trivial one-step thing, so it obviously terminates, but sequencing, if the two commands either side of a sequencing to each terminate, then obviously the sequence thing terminates. If then else, if the then branch and the else branch both terminate, then of course the if then else terminates. But the while loop is the crux of the matter, because that's where you've got a loop, and it's non-trivial to say when the while loop terminates. For those who know some computability theory, there's of course the whole famous halting problem that you cannot automatically algorithmically decide if a computer program terminates. You can't even always prove. Well, anyway, there are circumstances in which you can prove that a program terminates, but anyway, you can't, it's not algorithmically detectable whether or not a program terminates. Although once it's terminated, you notice that it's terminated. So how do we prove that a while loop terminates? And what we want to do, more than that, we want to prove correctness for a while loop with respect to a specification. So again, we're going to look for an invariant property that's invariant under the body C of the while loop. So in this case, but we also want to prove that it terminates. So a simple way of proving that a program terminates, so what I've got here is not the most powerful version you can have. This is a fairly simple way of proving that a program terminates, is that so in addition to the property that's preserved, the eta, the invariant property, how can we show that a program is going to terminate? Well, we want it to go around the while loop only finitely many times. Okay, so it needs to execute the C command finitely many times. So one way of guaranteeing that we can only go around the C loop finitely many times is if we can find a value that we can compute from the current store that has non-negative value, and every time we go around the C, every time we execute C, it strictly reduces that value. Because if you've got a variable with a non-negative value or some integer expression that has non-negative value, and if you reduce that value, strictly reduce it a number of times, there's only finitely many times you can strictly reduce it and remain non-negative. Okay, so the rule encodes that idea. So in order to apply the rule, we need to find some expression E that represents a non-negative value, some numerical expression, some like arithmetic expression that we can compute that represents a non-negative value. So that's the top left here. We're saying E is greater than or equal to 0. And we want that when we apply the body of the while command to it, it reduces in value. So how can we say it reduces in value? Well, we again use one of these ghost variables Z0 that doesn't appear in C, so it can't change value. We set it to the value of E before executing C, and we want the value of E after the execution of C to have gone down in value. So after execution of C, it's strictly less than Z0, but it's still non-negative. If we didn't bound it below by 0, we could decrease it infinitely often because we could go through negative values. But we want to keep it above 0 to make sure we can only go around that finitely often. So if that's the case, then clearly we can only go around the C loop finitely often for that to be true. And so, as long as we run the while loop in a state in which E is greater than or equal to 0, that expression that is decreased every time we run the while loop, but stays above 0, it can only be decreased finitely many times, which means we can only execute C finitely many times. So necessarily the while loop must eventually stop executing C, which means that B has to become false. Therefore, we'll exit the while loop and B will stop. Okay, so that's the idea here. And yeah, nicely, because E changes value. So we found the property related to the specification we're trying to show. That's called the invariant, as I said, because it stays the same. And E is called the variant of my total correctness rule because it changes in value every time we go around the loop. Okay, so I just want to end before the break by I seem to have the same slide a few times, but anyway. I want to end by giving you the total correctness version of the proof of. So I want to prove the same specification for greatest common divisor in total correctness logic. And here's what the while rule looks like in the tableau format. So it's exactly what you would expect. At the top and the bottom, we've got the precondition and postcondition of the while command, and indented, we've got the precondition and the postcondition of the body of the while loop of C. Okay, so here's the example total correctness proof. We want to show the same specification before, And now we're going to have to come up with, so we're going to do essentially the same reasoning as before, but we now want to come up with a variant. That's an arithmetic expression based on the variables we have. That is going to be, that will remain whenever we execute the C, that will remain positive, well, sorry, non-negative. Well, actually, in this case, it will even remain positive. And that will strictly decrease every time. So what would be such a variant in this case? Okay, XY. Yeah, I mean, X plus epsilon is fine. Very good. There are lots one could choose, but that's, I think, the simplest argument with X plus Y here. So that's indeed what I chose. Okay, so now we're going to have exactly the same argument again, except the variant stuff is going to, the new stuff is going to be in red. So at the start, we're making the assumption that X plus Y is non-negative in order to have the precondition and postcondition for the body of the while loop. We need to use the ghost variable Z0, so we introduce the ghost variable Z0. We want to show at the end of executing the body that X plus Y is now strictly less than Z0, and that just leads to basically we're just applying the rules as we had them before, and I'm just propagating all the time. I'm just propagating the new condition here. So for example, here where we've now got that 0 is less than, so X plus Y is non-negative and strictly less than X0. We wanted to show it's strictly less than X0. So what happens here? Well, we've got the assignment that this is the postcondition for X becoming, for setting X to the difference, taking Y away from X. So we're going to replace X with X minus Y here, but then we have X minus Y plus Y. So up here we get that the condition that X is strictly less than Z0. But that follows because above it we had that X plus Y is Z0 and Y is greater than 0. So of course, X is strictly less than Z0. And that's how it gets reduced. And yes, Faisal, yeah.
This don't be the need condition at the start that X is not equal to Y. Otherwise, again, it would be equal to Z0. Or is that only concerned inside of the loop?
So where were you expecting to put a condition?
Precondition. Or it's less than 0, but C0 inside of the loop, only inside.
And what property do you think might be missing?
X is not equal to 1.
Aha. No, but we've got while X is not equal to Y. We're inside the while, proving the while loop. So indeed, we have assumed that X is not equal to Y, where it says do precondition, and then that do precondition that then gets split into two because we have the if X is less than Y, or alternatively if X is greater than equal to Y, but because X is not equal to Y, I simplified that to X is greater than Y.
So it's less than C0 needs to hold only inside the loop.
It only needs to hold at the point that it's stated. So every statement is local to where it's stated in the program. So we're always saying this property holds at this point in the execution. So you imagine you're executing the program line by line, and in the while loop you might go round the loop many times. But anyway, every point you're executing a line, whenever you get to this statement, this property here will hold before you execute the statement, and this property here will hold after you execute the statement. That's how you read it. That's why this tableau style is so natural because you're always just reading, these are properties that hold at this point in the execution program. So maybe I mean, I don't think there's very much that needs to be said here, apart from that's the end of the proof. I guess, yeah, there seems to be an implied missing on the second line, but anyway. So that's the end of the proof. That's how a total correctness proof works. It's 10 o'clock, so we'll again have a break until 15:15, and then that's the end of Hoare logic. So we're now moving on to separation logic. For the last, I mean, it's the end of Hoare logic for now. Okay. Right, so what I want to do now, but is also going to be the main topic for next week, is introduce you to separation logic, which is a much more recent development than Hoare logic, but is based on it, and is a very powerful framework for reasoning about mutable data structures. So data structures, you know what data structures are, but mutable means ones that are implemented in program memory, and you can move pointers around and things like this. You know, actual data structures in memory that you can manipulate and change. So the Hoare logic that we looked at, we looked in the simplest possible setting, which is this very tiny programming language that, let me emphasize, all we had in it was integer variables. And as somebody pointed out in the break, this whole assumption that if you decrease something, if you decrease something infinitely often and it stays non-negative, sorry, we cannot decrease the value infinitely often with it staying non-negative. Of course, applies to integers, but would not apply if one had rational values or real values or something like that. So that technique exploited the fact that we were using integers. But anyway, the whole programming language and logic was just a very simple logic, programming language and logic for talking about programs on integer variables. So now what we're going to look at instead is data structures implemented in a very concrete way on a heap with pointers and manipulating pointers. And the use of separation logic for this is very powerful. It's very beautiful, but one could do a whole course on separation. I mean, I've said this for many topics. You could do a whole course on this topic. And of course, we've only got a couple of lectures on it. So we're going to just be dipping our toes in. But I'm going to try and motivate it through interesting programs. But unlike with Hoare logic, we're not going to actually do a complete verification, at least not this week, of any full interesting program. Rather, we're going to look at the program fragments and see what we can say about them in separation logic and what techniques we have in separation logic for dealing with them. But we're not going to take things down. We're not going to write like full derivation trees on the board and this sort of full tableau proofs, because it would just be too big. So to motivate it, we're going to, as I say, we're going to be looking at essentially data structures implemented in memory using pointers. And we're going to have as our first motivational program the following one. So our variables are still going to take integer values. And here, nil is some chosen integer that I've chosen to represent the empty list. Okay, so we're going to represent data structures in pointer memory with some data values playing special roles. So nil is just some chosen integer that I've chosen to represent nil. And then we're going to go into a while loop. So while I is different from nil, we're going to perform a sequence of things. We're going to perform that. So what this is doing is we're interpreting the integer value I as a pointer And we're setting k to be the value of the cell pointed to by pointer I. We'll have a look at an example in a moment of this in execution. And this is, likewise, we're considering I plus 1 as a pointer, so we're doing arithmetic on pointers. So I is going to be a pointer, I plus 1 is also a pointer. And we're now setting the, not I plus 1 itself, but the value of the cell pointed to by I plus 1, we're setting to j. J we're going to now set to I, and I to k. Okay, so a little mysterious program. But what's it doing? Well, let's execute it on a tiny example. So we're viewing ourselves as having like memory with pointers, which we're going to call the heap. And the cells are actually given integer addresses. So let's suppose this one's 100 and this is 101. This is going to be the implementation of a list, right? A linked list. So, for example, we might have 3 in here. And then this, here we're going to have a pointer to the next. And suppose this is 200. Doesn't matter. This is 201. So this is say 7, and then 201 we've got that. Okay. So classic linked list in which you use a pair of cells to, you have the data value followed by a pointer to the head of the next list. Hands up if you've seen linked lists like this before. I mean, yes, good. That's reassuring. Right, so we're going to apply the program to this. So of course, here, by this pointer, this is how one would draw things, but let's see what's actually going on. So of course, here we mean, in this cell, we've got the address 200, okay? That's what the pointer means. And we're going to run this program, starting with, let me get my notes. So we always run it, starting with some value I. And the idea is we're taking I to be we're taking I to be a pointer to the start of a list. Okay, so here it's the start of this, the head of this list. We're pointing to the head of this list. Okay, let's run the program on this. So the first thing we do is we set j to nil. I'm just wondering where I want to put. I don't think I want those to be up in the air. I think I just want them to be doing that. So we've got I is 100, j nil. These are variable values. And so what do? We take the contents of cell 101 and assign that to the variable k. So that's 200. So k at this point becomes, let's put k a bit to the right, because k is a bit more auxiliary. So k is 200. We take the contents of cell 101 and update them to j. Okay, so we replace the contents of the cell 101 with j, and j is currently nil. So this one becomes nil. So nil, as I said, is just some integer value representing the empty list. We set j to be I. So j becomes 100. And we set I to be k. So I becomes 200. Oh. So we've only modified that, haven't we? So actually, rather than doing that, I think I want to. I wanted to show the evolution of how things are going. So here it's got 7 and nil. This became nil, and this is 3. Okay. All right. So at this point, we go back to the while loop. So while I is not nil, well, it's still not nil. So k becomes the contents of I plus 1, which is the contents of 201, which is, so k becomes nil. We set the contents of I plus 1, that's the contents of 201 to j, which is 100. We set j to become equal to I. So j becomes equal to 200. And we set I to be k, which is nil. And now we've completed the body of the while loop, so we go back to the beginning while I is not equal to nil, but now I is nil. So we come out with j being 200, and with this in the heap. So can anyone see what this is doing? Yeah, very good. Sorry, who said that? Yeah, okay, very good. It's reversing the list. Now, here we've got a pointer. So our j is pointing to here, and here we've got a pointer to like this. And you know, I made it as short as possible, but you can check for yourself that it's actually reversing a list. And let's call this program P, or let's call it R, or rev. And that, actually, let's call it rev of I, because I is the important input. So it's reversing the list that is pointed to by I. And at the end, you get pointed to the reversed list. So how could we specify, how would we like to be able to specify this program using a Hoare triplet? Well, we'd like to say something like this. We'd like to say that if we start in a state that satisfies let's use a capital, some property that we need to define, but it says I is a pointer to a list, so it would be true in this original state here. It wouldn't be true. It probably is anyway. It doesn't matter. I think it is actually an invariant property that goes with the program. So if I is a list, then if we run the reverse program of I, that just means putting this whole program here, then, well, the problem is, it's a bit, then j is pointed to a list, but how can we say that j is the reverse list of I? So this doesn't quite work. What we need to say is we need to give ourselves a richer mathematical language. We can say if I is a pointer to a list L, then j is a pointer to reverse of L, where here the idea is L is a mathematical list. So it's actually a mathematical sequence of numbers. L is a mathematical list, not a list implemented in data in heap memory, but an actual sequence of numbers. And reverse is the mathematical reverse function. Okay, and then so list IL says that I points to the head of a mathematical in our heap memory. Well, sorry, the head of, sorry, that's wrong. The head of a linked list, in heap memory, whose mathematical list is out. So, for example, I guess point. Well, so the list, a special case would be list nil of the. So this is our number representing the nil list. This is true. Although there's no pointer involved, so the pointing to is it's a little bit vague here. But so this would be true, and list of our starting state there. So 100, 101, 200, 201, 3, 200, 7, nil. This is true, but list of sorry, this. So this should be list 100. I'm really sorry. This should be list 137 is true in our starting heap memory there. In our starting heap memory. But list of same starting point of 7.3 would be false, and also list of 101 in 3.7 would also be false because 101 is not the pointer to the start of the list, and we can make sure of that by making sure that 102, for example, maybe just loops back to itself. Okay, so I'm just concocting something to make sure that if we pointed to 101, then we wouldn't get a list at all. Okay, is that clear? But the point is, we need a much richer logic in order to be able to say these things, but we'll take that for granted, okay? That we can state these things like this. This list is this number, given our heap memory, is indeed encoding a list. So the programs involved the programs that we're working with involve ordinary memories, or ordinary variables like the I and J that we were using. ordinary variables, so I, A, so on, taking integer values. Plus a heap memory. And so to model this, we require two things. We require a state. For the ordinary variables, so that's a function. Function from variables to integers. And also a heap, where a heap, H, is the sort of thing I was drawing in boxes, so like the heap is something like we had before. So a heap involves pointers. So a heap has addresses in memory, and the addresses in memory contain numbers. And only finitely many addresses will be assigned values. So the heap is going to be a partial function. I mean, we could put it on the be a bit funny having negative addresses, so let's make it from natural numbers to integers. So a partial function defined on only finitely many values. So this would represent this particular implementation of a list is the partial function 100 maps to 3, 200, sorry, 101 maps to 200, 101 maps to 200, 200 maps to 7, and 201 maps to 0, whatever our chosen integer value was. Because as I said at the start, we're choosing a number to represent nil. Okay. So that's the setting. This is how we're modeling our programs that manipulate memory in a memory that involves a state that's the value of variables, and a heap, which is this pointer, this kind of memory that involves pointers given by addresses and integer values and so on. Okay, is that clear? And then this predicate list, and indeed any predicate, any property will be true in a state, true or false, depending on the current state and heap. So our assertions, so we have, maybe I can rub this off. So we have some language of assertions. Assertions 5 represent properties of the pair SH. S is the state, and H, say. And the whole triple or triple by, let's again use C psi in separation logic. Says, so this is, so we have that specification. If we start off with a list in memory and we run our list reversal program in memory, our in-memory reversal program, then at the end we got back the reverse this in the memory. That was the whole triple. What's that officially say? Well, it's similar to the whole triple we had before, but a little bit more subtle. So it says, if phi is true, or let's do it. Suppose, a bit like this, suppose we execute C from an initial state and heap combination such that I'm going to use logical symbols, but phi is true in the state heap combination. That's what that says. Then we're going to do the partial correctness assertion. The partial correctness says, if C terminates, then so in a state heap combination S prime H prime, then the post condition psi is true in the state heap combination. But it turns out in order to get the logic to work, for which one needs some quite important properties, some of which we'll talk about. But this form of partial correctness is not quite enough. Well, now we're manipulating memory. We have various ways that the program might do things that we don't want to do. One is that it will go into an infinite loop, which is what we had in the original while program. But another way that a program can do something we don't want it to do is we can have a memory fault. Now we're using these heap memories, we're manipulating the heap memory. We might try to access a cell that's not as allocated in the heap memory, for example. I think that's really the main way in which one gets a memory fault here. Now, you should write programs so that such things don't happen. And whereas termination we might allow ourselves to show termination separately. Really, in order to get a working program, you really don't want it to run into any memory faults. So we are going to actually make it require that the specification does guarantee that we don't get a memory fault. So the execution is, well, there's a word for this, is safe, meaning does not access, well, does not cause a memory fault, which means trying to access an unallocated heap cell. That does not cause a memory fault. Okay, so with this, we can now understand our original specification for the list reverse. It says, if we started off with a heap with a variable I, that's a variable in the state, whose value points to the head of a list in the heap. Well, that represents a list, meaning it is either nil or its value points to the head of a non-empty list in in the heap, and we run the program, then no memory fault will occur. Termination we need elsewhere, if it does. This program might not terminate if it's following loops around. I'm not quite sure. I'm not quite sure of how termination works. I didn't think it through for that program. But anyway, if it terminates, then indeed it will be the case that the resulting value of j is indeed either nil or the pointer to the head of a linked list in the resulting heap. And moreover, the list that is stored in the heap memory is the reversal of the original list. Okay, so all that is quite a lot, tidied up in a nice small package. And so what I want to talk about is then what tools. So I hope you agree with me, such things are useful to verify. And there's a whole lot of there's a huge amount of the huge industry of applications of such things. I mean, like the whole of WhatsApp's code has been verified. Well, when I say the whole of it, but anyway, there's a big separation logic team that's gone into the verification of WhatsApp code. So that's one example of code that's been verified using separation logic. Right. So I want to talk a bit about the technology involved. We don't have very long. Yes.
Isn't ordinary.
A variable that isn't ordinary. So what do you mean?
I don't know what it means variable is.
Oh, sorry. Right. Okay. So when I said ordinary variables, I wasn't thinking that there also exist extraordinary variables. I was thinking more just the same kind of variables that we have in the while language. So they're modeled in the same way we have. So variables are given values by a function, wherever it is, like this. So variables take values. So I wasn't meaning that there's something, there are also extraordinary variables. There's more that this is what we're familiar with, whereas the heap is something we're not familiar with. In addition to that, we have the heap, which we access through integers, which are giving us the addresses, and through ordinary variables to access it. But we're accessing it using, in the notation I was using, these square brackets to say, rather than modifying the variable, at that point, we're modifying the contents of the set. Okay. But yeah, good question. But I didn't mean it that there were also some notion of what extraordinary variables. Sorry, it's misleading how I phrased it. Okay, so a crucial thing in separation logic is we want to follow we want a means of verifying programs that is methodologically viable, and really the only methodologically viable way of verifying is to be able to verify according to the program, following the program structure in this modular way, like in Hoare logic. So in Hoare logic, to verify a sequence, we broke it down into two verification steps, one involving either part of the sequence statement. So again, we want to do the same thing with these languages for heaps. And that means we need to have some way of controlling how different fragments of a program access the heap. And the crucial thing that separation logic introduces for that is a notion of separating product that talks about properties holding on separate parts of the heap. So, Vasilia.
Can we represent any data structure with this heap?
Well, we've seen a list. It's easy to see. I mean, any data structure that you can implement with pointers can be implemented in a list, because it's basically, it's basically giving us pointers. So so one's used to implementing data structures with pointers in computer programs, and so I mean, basically the normal data structures are typically implemented in this way. But here we're looking actually at the concrete implementation so that we can reason about it. So for me, I think for everyone, the really critical thing in separation logic is a new logical connective called the separating conjunction. So our properties are talking about the stating properties of variables together with you have a state of variables, the current state of variables, and the current heap state. And we'll have expected properties like the conjunction of two properties is true. Obviously, if and only if. So, in defining how to interpret formulas, we'll define these in the usual way. The usual definition of satisfaction. But because we've got this heap component, we can also make new logical connectives whose truth depends specifically, is related specifically to the heap structure. So the crucial one is this, that this says phi and psi are both true, but they're true on separate areas of the heap. So this says we can partition H as H1. People tend to use star for this, H2. Such that phi holds on H1 and psi holds on H2. Right, so there's not much time left, so I think I'm not going to get very far today. So I think what we'll do is we'll just do some examples of how this, some simple examples of how this works, and then we'll see, we'll see what it's saying. So it's a kind of conjunction because both phi and psi are true, but they're true on separate parts of the heap. And we also introduce another construct, which is like this, which says that, so this says n is a pointer whose associated cell has value v. So formally, that's saying that h of n is defined, it's a partial function h, the heap, defined on only finitely many values, but in this case it is defined on n, and h of n is b. Okay. Oh, hang on. So it says it is defined only. There are two flavors of separation logic, which I think for this course we'll do this one. Is defined only on n, and h of n equals b. Okay, so So 100 maps to 7 is true in the heap. We've got cell number 100 and its value is 7. But it's false in the heap 100 is assigned to as 7 and 101 takes value 2. Okay? So it means it's very precise. It's the heap only has this value. And you might say, well, that's a bit restrictive. When are we going to be able to use that? But if we want to say the heap has the value 7 at 100 and other values, we can say, we can instead look at 100 maps to 7 star true. So this says, and we can divide the heap into 2 portions, one of which this is true, and then this one, just 100 is going to be allocated, and this is true here. And then the other one, true, is going to be true, which is always true. So this is true in the heap, in this heap. Okay, so simply we've got a property that says, only the cell 100 is allocated and its value is 7. But we can say that the value of 100 is 7 and some other cells are allocated by using the separated conjunction. Because this is true if we can split the heap into 2, which we can here, take 200 in one part and just 7 in the other, such that on one part only 7 is allocated and on the other, whatever happens, it's true as well.
This one is first one.
Yes. It is true in both cases. Because we're splitting into, the other one is the empty heap. So we have another important thing, empty, which is defined if and only if H is the empty heap. It's true if and only if H is the empty. Well, so actually, what I'm going to do is I'm going to put a link to a very nice, friendly survey article that was published in the Communications of the Association of Computing Machinery, the American ACM, a few years ago, I think 2019 or something like that, about separation logic for you to look at over the next week, and you'll get some flavour of the separating conjunction from that. And then when we start again next week, we'll start with the separating conjunction and how it's applied to program verification. But here, I mean, to end today, we've got the definition of these important the separating conjunction, the one cell is allocated and the empty heap property. And next week we'll see how we can use such things. Okay, are there any questions for today? Good. So see you next week. And thank you for showing up today in the virtual holidays.